Today is part 2 of lesson 4.9, and the title of our lesson from yesterday is Roots and Zeros. Where we've been is we found roots of polynomial equations. Today we're going to be finding zeros of polynomial functions. And really you can think of these synonymously. We just typically say that equations will have roots and functions will have zeros, but bottom line is, in both cases, we are trying to find the values of the variable that when we find certain numbers, plug those numbers in for variables, they should give us 0. Whether that's the equation, they should make an equation equal 0, or if we input those numbers into a function, they should cause the function to become 0. So today our focus is going to be my second objective here. The issue with today, however, unlike last night where you were able to do various types of factoring in order to come up with the roots of polynomial equations, today, factoring is not going to be possible in order to come up with the zeros of the function. So we're going to have to resort to a different method in order to come up with the zeros of these polynomial functions. So that's going to be the emphasis of today's lesson. So let's get started with some examples, and you're going to be doing these problems that they look a lot like what we're about to do. And as you can see, here we have this function, h of x. It is not factorable. So we're going to rely on something called the rational root theorem. Very important theorem. You're going to see this again for those of you who are headed to pre-calculus. So hopefully you'll get some good practice with it this year, and it will stick with you for later. But the rational root theorem basically says this. We're going to make a fraction first of all, and in the top of this fraction we're going to list all of the factors of this last number that we call the constant. So all of the factors of 4, positive and negative, we can just list them like this: plus minus 1, plus minus 2, and plus minus 4. Okay, below, the bottom part of this fraction will contain all of the factors of what we would call the lead coefficient, the number that's in front of x cubed in this case. And of course that's an invisible 1, so the factors of 1 are just plus minus 1. And we're going to intentionally give you only problems this first go around where this lead coefficient is going to be 1, so that reduces it makes this fraction quite a bit easier to deal with. Well, if you notice, since there's really 6 numbers in this numerator, and they're all over 1 or negative 1, which really means that the result of this fraction is just going to be these numbers, because a number over 1 is just the number. So what do we do with those numbers? Well, the rational root theorem now is going to lead us, taking these numbers, is going to lead us to what we might call, some people call the rational root test. Okay, so these 6 numbers, just to illustrate, I'm going to list them down the side of what we would call a table. Whoop. Fix that. I'm going to make a little table, and we're going to use something that we've been practicing with here lately. We're actually going to use synthetic division. So here are my choices. You can think of these as possible roots or zeros to this function. They're possibilities for rational numbers anyway. And then across the top, think about synthetic division, how you would set it up. Remember, we only use the coefficients from the polynomial and the constant. And now we are going to be doing synthetic division, but it looks a little different. It's set up a little bit differently than what we've seen in the past, but it's really the same principle. Remember, we begin by bringing this first number down below the line, when we were doing synthetic division before. And then this number below the line would always multiply times a number that we said was in the house. Well, this number over here to the left is that number in the house. So when I multiply, I'm going to multiply 1 times 1. And remember, with synthetic division, we always add after that. So I'm just going to multiply 1 times 1, I get 1, and now I'm going to add to the next number. So 1 plus negative 1 is 0. Okay, and this is repetitive. We're going to do that same thing again. This time I'm going to multiply 0 times 1. That's 0 plus 2 is 2. 2 times 1 is 2, plus 4 is 6. Okay, so the goal of this little table, this rational root test, if you remember in synthetic division, this last number represents a remainder. So we're trying to find the number, these possible choices that we got out of the rational root theorem. We're trying to find the one that gives us a 0 remainder, and that will be called a 0 of the function, or if this were an equation, it would be called a root of the equation. Well, 1 isn't one of my 3 zeros, so I'm going to keep looking. I'm going to test negative 1. So again, I'm going to bring down 1, multiply negative 1 plus negative 1 is negative 2. Multiply negative 2 times negative 1, that's 2, plus 2 is 4. Multiply again, negative 4 plus 4 is 0. So I have found one of the 3 zeros of this function. It's negative 1. So I'm going to find the other 2 by taking these numbers. If you remember in synthetic division, we could use these numbers to make a polynomial. These are coefficients, and this is a constant. So these 3 numbers form the following quadratic equation. Okay, and so now we're in familiar territory because we should be really good at solving quadratic equations. This does not factor, but we could always use the quadratic formula, or you could complete the square if you so desire. I'm going to use the quadratic formula and do the opposite of b, plus minus the square root of b squared minus 4 times 1 times 4 all over 2 times 1. And 2 plus minus, that's the square root of negative 12 over 2. And now we'll work on simplifying the square root of negative 12. And that's 2i square root of 3 over 2. And now we can reduce because we're all of these, of course, are divisible by 2. So 2 divided by 2 is 1, plus minus 1i square root of 3, and then that's all over 1. So we don't need that denominator. So we have found now our 3 zeros of this function. We have a rational number, or we could call this it is a rational number. It's also obviously real. And then we have 2 imaginary or complex number solutions, one plus I root 3 and one minus I root 3. So when factoring isn't possible and we're dealing with something that's third degree or higher, then we can resort to this, what we might call the rational root test, applying the rational root theorem and utilizing synthetic division. Okay, let's try another one. Now letter B represents a unique opportunity to save ourselves some time. If you can, in the future, you might want to just pay close attention to when you're asked to find the zeros of a function like this, find all of the zeros of a function, and factoring isn't possible. Just notice that if you take these coefficients 1, 2, and 9 and multiply them together, you end up with the constant. So this doesn't happen every time, but when it does, it will save you the time from having to test all of the numbers that we would get out of the rational root theorem. So I'm going to show you the result of the rational root theorem again, just so you can get used to it. All the factors of 18, plus minus 1, 2, 3, 6, 9, and 18. 1, 2, 3, 4, 5, 6. There's 12 different possible rational roots for 18. So here's what makes this nice. When I call this the pattern. When you see this pattern where the coefficients multiply together to give you the constant, then the number out of this list the only number that you need to use for synthetic division will be the opposite of the quadratic coefficient. So the quadratic coefficient is 2. I'm going to use -2 in my division. It saves me the time of hunting for it. Now I will say this, I didn't really mention this in class, but here's another, if my pattern did not hold true. Let's say that this was a 6 here instead of 9, and the coefficients did not multiply together to give you a constant. This is always something else that you can think about. Any little tip that you can use to cut down on the time obviously is helpful, because sometimes these can take a few minutes before you find a 0. Notice all the signs in this are plus. Every term is positive. So whenever that happens, you need to choose a negative number to test. Okay, so that will save you a little bit of time. Now that's, of course, in this case our pattern holds true, so we knew which number to test. But anytime you're given a function and all of the terms are positive, then you need to test a -0. And that'll cut your number of tries in half anyway. So let's just go ahead now. We still need to do the synthetic division. So let's bring down the 1, multiply, -2 plus 2 is 0, 0 plus 9, -18 plus 18 is 0. We knew -2 had to be a root. Now these numbers, remember, remainder 0, 9 is the constant. There is no linear term, but there is a quadratic term. So I'm going to take x squared plus 9, and I'm going to solve this quadratic equation for the other 2 zeros. So I subtract 9 from both sides, and then I do the square root of both sides, and I get my other 2 zeros of this function, positive 3i and negative 3i, to go along with -2. All right, so let's try one more cubic function. Unfortunately, these do not multiply together to give me the constant. That would be great. So I'm going to have to come up with a list, all the factors of -15. That's not too bad. There's only 8 choices. So let's just start. You don't have to make an entire list. You can just write them down as you go about testing them. Okay, so we can start off with 1. Bring down the 1, multiply, add. It's -6. Multiply, -6 plus 17 is 11. Multiply, 11 plus -15 is -4. So I know that 1 is not one of my roots. So maybe we can test -1. Bring down the 1. -1 plus -7 is -8. This would be positive 8 plus 17 is 25. And -25 plus -15 is -40. Okay, well, let's try 3. Bring down the 1, multiply. 3 plus -7 is -4. -12 plus 17 is 5. 15 plus -15 is 0. So we found our first 0. It's a rational number. It's a real number, of course. Now let's find the other 2. Using these numbers, we're going to make a quadratic equation. You can always remember that if you divide it into cubic, we call this the recessed polynomial. It will always be 1 degree less. Okay? When you do this synthetic division process, you will always have a polynomial that is remaining, that is left. The remainder is 0. But this polynomial will be 1 degree less than your original. Okay, so let's solve this quadratic equation. It doesn't factor, so once again, I think I'm going to complete the square just because some people need to see this. I'm going to move the 5 over. X minus 2 quantity squared. So let's add 4 to both sides. Negative 1, square root of both sides. The square root of negative 1 is I, plus minus. And now we're going to add 2 to both sides. 2 plus minus I. Okay, so that represents 2 of the solutions, 2 plus I and 2 minus I, to go along with the real number 3. Okay, so hopefully that's good on the cubic. Well, let's go up a notch. Let's try some quartic polynomials. All right, so rational root theorem. Let's list the possible rational roots, the factors of negative 40, plus minus 1, 2, 4, 5, 8, 10, 20, and 40. Boy, that's a big list. That's a lot of numbers to have to test. And we don't have to test every one. As soon as we find that initial 0, then we could use that to help us find the next one. But this quartic means that we're going to have a little bit more work involved than we had in the previous cubic examples. Okay, so make our little table here. 1, negative 6, positive 6, 24, negative 40, and you can start anywhere you want, really. I usually just start with 1, see what I get. 1 times 1 is 1, plus negative 6, negative 5. Negative 5 plus 6 is 1. 1 times 1 is 1, plus 24 is 25. And 25 plus negative 40 is negative 15. All right, if you want to go with a negative, you could. Just do the opposite, and so what we get. Negative 1 plus negative 6. Positive 7 plus 6. Negative 13 plus 24, 11, negative 11 plus negative 40, negative 51. All right, let's try 2. Bring down the 1. 2 plus negative 6 is negative 4. Negative 8 plus 6 is negative 2. Negative 4 plus 24 is 20. 40 plus negative 40 is 0. So we found our first 0 of this function. Okay, now we got to find 3 more. So this, we started off dividing into quartic, and so we should have a cubic polynomial that remains. Squared minus 2x plus 20 equals 0. All right, so now we're going to do this process again, but this time we're going to use the factors of 20. Okay, rational root theorem. Not quite as many. All right, and so we're going to go through this process again. Set up my table. 1, negative 4, negative 2, positive 20, and start testing. If you bring down 1, 1 times 1 is 1, plus negative 4, negative 3. Negative 3 plus negative 2, negative 5. Negative 5 plus 20 is 15. All right, so negative 1 plus negative 4, negative 5. 5 plus negative 2 is 3. Negative 3 plus 20, 17. Okay, so let's try 2. 1 times 2 is 2, plus negative 4, negative 2. Negative 4 plus negative 2 is negative 6. Negative 12 plus 20 is 8. Using negative 2, we get negative 2 plus negative 4. 12 plus negative 2. Negative 20 plus 20. We have a winner. All right, so our other 0 is negative 2 to go along with positive 2. All right, so what remains is a quadratic. We divide it into cubic, so now we have a quadratic equation. And now we're in familiar territory. We don't have to go through the table anymore. We're just going to we can't factor this, so we're going to use the quadratic formula or completing the square. I guess I'll go back to quadratic formula. B squared minus 4 times 1 times 10 all over 2. 6 plus minus, this is the square root of negative 4 all over 2. Let's come over here. 6 plus minus 2i over 2. And now we can divide 2 into these, and that's 3 plus minus I. So we needed to find 4 roots, and we did. 3 plus I, 3 minus I, negative 2, and positive 2. Okay, that took a few minutes, so I'm going to erase this and work on letter E. Hopefully you have all this down in your notes. If not, you can rewind it and pause it if you need to. And let's try, I just have one more example, and then I'm going to let you practice a few of these. There's not too many that you need to do. But as you can see, sometimes they might take a few minutes. Okay, don't see the pattern, so I'm going to write out the factors of negative 3. That's pretty easy. So I don't have a lot of numbers to test. And I'll start with 1 and then list the coefficients and the constant. And let's see, 1 times 1 plus 2 is 3. 3 plus 2 is 5. 5 plus negative 2 is 3. 3 times negative 3 is 0. It's always nice when we find a 0 right off the bat. And what remains is x cubed plus 3x squared plus 5x plus 3 equals 0. So remember what I said earlier, if all of the signs, I didn't really get a chance to mention this in class today, if all the signs are positive, then we need to choose a negative to test. Okay, so that means I'm either going to test negative 1, well, I'll start with negative 1, and then if that doesn't work, I'll try negative 3. It's got to be one of those. All right, so 1, 3, 5, 3, because we had the same base. I know it's negative 3, but positive 3 has the same factors. So let's try negative 1. Bring down the 1. Negative 1 plus 3 is 2. Negative 2 plus 5 is 3. Negative 3 plus 3. Sure enough, our other 0 is negative 1. So these numbers make a quadratic equation. Okay, and there are no factors of 3 that add up to 2. Can't factor it. So once again, we'll use either the quadratic formula or completing the square. So let's just do the formula. Opposite of b plus minus b squared minus 4 times 1 times 3 all over 2. All right, so let's see if we can skip a step here. This is the square root of negative 8. And if I simplify that, that's 2i square root of 2. And then canceling out the 2's, we end up with our final third and fourth answers. Negative 1 plus minus, let's put it here, I root 2. Okay, after we simplify. Negative 1 plus minus I root 2 to go along with positive 1 and negative 1. Okay, so that is all we got covered today. I've got a little bit more from lesson 4.9 that I need to cover, but we're going to save that for a later time. So I hope this helps. If you have any questions, let me know.